Welcome back, everyone, to another deep dive into the online encyclopedia of integer sequences. If you're working through number theory, you know the OEIS is just an incredible resource. We're continuing our series today.
And today we're looking at a sequence that, well, it seems pretty straightforward on the surface, but it's got some really interesting properties. A0000194.
Right, A0000194. The title is Nearest Integer to Square Root of n.
Exactly. It starts off 0, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, 3, 3, 3, 4.
And yeah, that repetition just jumps right out, doesn't it? You see 1 twice, then 2 4 times, 3 6 times.
Mm-hmm. That's the immediate hook. Why this pattern?
So that's really our core question for this dive. What's the rule generating this, and why this very specific growing repetition?
Well, the definition itself is quite neat. For any non-negative integer n, the term an is simply the integer that's closest to the square root of n.
Okay, closest integer, so like rounding.
Pretty much, yes. Standard rounding.
Can you maybe walk us through one or two quick examples, just to make sure we're on the same page?
Sure. Let's take n equals 2. Square root of 2 is what? About 1.414.
Right.
The closest whole number to that is 1, and that's the term a2.
Okay, makes sense.
Or maybe n equals 7. Square root of 7 is roughly 2.646.
So the nearest integer would be 3.
Exactly, and that's a7. So you see how the rule generates the terms?
I do, yeah. But it's connecting that simple rule back to the pattern of repeats that's the interesting part.
Ah, yes, the pattern. Why does each integer k show up 2k times for k1 or more?
Yeah, why that specific number?
Okay, think about it this way. For an integer k to be the nearest integer to the square root of n, the square root itself has to be closer to k than to k1 or k plus 1.
Right. It needs to fall within a certain window around k.
Precisely. Mathematically, that means the square root of n has to be between k minus 0.5 and k plus 0.5.
Okay.
So k 0.5 squared must be less than n, and n must be less than k plus 0.5 squared.
Right. You square everything to look at n itself.
And if you expand those squares, you get k squared minus k plus 0.25 is less than n, and n is less than k squared plus k plus 0.25.
Okay, so n is trapped between those two values. And since n has to be an integer.
Exactly. That's the key. The smallest integer n can be is k squared minus k plus 1.
Right, because it has to be strictly greater than a k2k plus 0.25 value.
And the largest integer n can be is k squared plus k.
Okay, so the range for n is inclusive, from k2k plus 1 up to k2 plus k.
Correct. Now, how many integers are in that range? You take the upper bound, subtract the lower bound, and add 1.
So k2 plus k minus k2k plus 1.
Yeah.
Let's see, the k2 cancel. K minus k is 2k minus 1 plus 1 cancels.
It simplifies very nicely.
It just becomes 2k.
Exactly. So for any k that's 1 or bigger, it appears 2k times in the sequence.
Yeah, okay. That explains it perfectly. 1 appears 2 times 1 2 times. 2 appears 2 times 2 or 4 times. 3 appears 2 times 3 equals 6 times.
Yeah.
Brilliant.
It fits together quite elegantly.
What about the very first term, the 0? Does that follow the 2k rule?
Good question. No, k0 is a special case. The square root of 0 is 0. The nearest integer is 0. That only happens for n0.
So 0 just appears once at the start.
Correct. The 2k rule holds for k greater than or equal to 1.
That really ties it all together. Okay, so that explains the core definition and the pattern. But the OEIS page, as always, has more. It mentions alternative definitions, formulas.
Yes, there are several ways to express this sequence.
One was the oblong-root. That sounds intriguing.
Right, the oblong-root, it connects to oblong numbers of the form k times k plus 1. Think 2, 6, 12, 20.
Okay. Products of consecutive integers.
Yes. The oblong root of x is defined as square root of x plus 14 minus 12. And it turns out our sequence an is just the ceiling of this oblong root of n.
Ceiling, meaning round up. So an, or ceiling squared again, plus 14, 12. How does that relate back to the nearest integer idea?
Well, it's essentially capturing the transition points. The nearest integer changes from k to k plus 1, roughly halfway between k squared and k plus 1 squared. This oblong root formulation, especially with the ceiling function, accurately captures where those transitions happen. It's another way to frame the same rounding behavior.
Interesting. It also gives a formula using the floor function, which looks quite different. An on floor 1/2 times 1 plus square root of p is 4/9.
Oh, yes. That one might look less intuitive at first glance.
Definitely.
But it actually comes directly from solving those inequalities we worked out earlier, the k 0.52n, k plus 0.52 part. If you solve for k in terms of n, this formula emerges.
Okay. So it's derived from the same core idea, just rearranged algebraically.
Precisely. And it avoids having to explicitly think about rounding. The floor function handles it after the algebraic manipulation.
There's another floor formula listed too, which maybe feels a bit closer to the original idea.
Right.
an floor squared en plus 12.
Yes. That one is probably the most direct computational translation of newest integer.
How's...
Well, think about standard rounding. If the fractional part is less than 0.5, adding 0.5 won't push it over the integer threshold before you take the floor.
Right.
But if the fractional part is 0.5 or greater, adding 0.5 will push it to or past the next integer. Then the floor function gives you that higher integer.
So adding 0.5 and taking the floor is just a neat trick to implement rounding.
Exactly. It's a very common way to do it computationally.
It's fascinating how these different mathematical closed ceiling of an oblong root, these floor formulas, all describe the same sequence.
It shows the richness of even seemingly simple concepts.
The entry also loops back, saying A0 and AN k for n in the interval k2k plus 1 kk plus 1.
Yes, that explicitly connects back to our derivation of the 2k repetition count.
And it links that interval to other sequences, A0002061 and A0002378.
That's right. A0002061 gives the starting points of those intervals, the k2k plus 1 values, and A0002378 gives the end points, which are those oblong numbers, pk plus 1.
So our sequence, A0000194, is basically telling you which of these consecutive intervals, defined by those other sequences, the number n falls into.
That's a great way to think about it. It partitions the integers based on their nearest square root.
And the cross-references don't stop there. The list is quite long. A0000037, the squares themselves, A0000024, A0531887, A0531889, A2599351.
Loads of them.
Yes, the OEIS is brilliant for showing these interconnections. It maps out the relationships between different number patterns.
It also contrasts A0000194 with A0000196, which is just floor, and A0003059 ceiling square in.
And that comparison is very useful. It highlights the difference. Our sequence uses standard rounding, while the others always round down or always round up. Subtle changes in definition lead to distinct sequences.
It really shows how precise you have to be in mathematics.
Absolutely.
Now, the entry also hints at some deeper waters. It mentions connections to the general Pell equation and reduced quadratic forms. That sounds quite advanced. It does touch on more advanced number theory, yes. Pell's equation involves finding integer solutions to equations like by 2 dy2 UL 1. The properties of square roots and how integers approximate them, which is core to our sequence, can be relevant in analyzing solutions to such equations.
So the behavior of this simple rounding sequence has implications in solving Diophantine equations.
In some contexts, yes. We won't dive deep into that today, but it's good to be aware that these elementary sequences often pop up in more sophisticated problems.
And similarly, there's a mention of a generating function involving Romanujan's two-variable theta function.
Ah, yes. Generating functions package a sequence into a single function, often a power series. Finding that the generating function involves something as significant as a Romanujan theta function, well, that points towards connections with modular forms, elliptic functions, really deep areas of mathematics.
Wow. Again, showing the unexpected reach of a sequence defined by simple rounding.
It's a common theme. Basic operations can lead to profound places.
Shifting gears slightly towards analysis, there's a comment about the sum of reciprocals. Summing 1 over an to the power s.
It relates the sequence to the Riemann zeta function.
The Riemann zeta function. Okay, that's definitely a big name in number theory.
Indeed. The result mentioned, summon 1 ans equals 2 times zeta s1 for s2.
So summing the reciprocals of our sequence terms, raised to a power, directly gives a value related to the zeta function.
Yes. It connects the discrete term-by-term behavior of our sequence to the analytic properties of one of the most important functions in mathematics, one deeply tied to prime numbers.
That's quite a connection, from simple rounding to the distribution of primes in a way.
It hints at the underlying unity in mathematics.
And finally, on a practical note, the entry provides code snippets. Maple, Mathematica, PARI, Haskell, Python.
Which is very helpful. It shows people how to actually compute the sequence easily.
Right, makes it accessible for computational exploration for students testing things out.
Absolutely. It grounds the abstract ideas in something concrete you can generate and play with.
Well, this has been quite the journey for A000194. We started with just nearest integer to the square root of n and this funny repetition.
And we ended up touching on everything from basic inequalities to oblong numbers, floor functions, Pell's equation, theta functions, and the Riemann zeta function.
Yeah, it really drives home the point that you shouldn't judge a sequence by its initial appearance. There's often a lot hidden beneath the surface.
That's the beauty of the OEIS, isn't it? It's full of these gems.
So as we wrap up this deep dive, here's maybe a thought for our listeners to mull over. We know the perfect squares get farther and farther apart as numbers get bigger. How does that increasing sparseness of squares affect the length of those runs of 2k terms in our sequence?
That's a good question. Think about the intervals k2k plus 1, k2 plus k. As k increases, how does the length relate to the gaps between squares?
Right. What does that imply about the density of terms or how the sequence behaves way out on the number line? Could that relate back to some of those deeper connections we mentioned?
Something to ponder. It encourages looking not just at the definition, but the large-scale structure.
Definitely. We encourage everyone to click through those cross-references on the OEIS page for A0000194 and keep exploring. Thanks for joining us for this deep dive.